Hello, I'm Nachin Guan from the Data Systems Group at the University of Toronto. Here, I'd like to introduce our work, VILA Online Auditing of Machine Learning Model Accuracy and the Finite Labeling Budget. Our work focuses on evaluating the accuracy of machine learning models deployed in a pipeline. A machine learning pipeline usually consists of multiple stages, including data extraction, model training, model evaluation, and deployment. Usually, we first train a machine learning model using some training data. Then we evaluate our model using holdout test data. If the model performs well, we deploy it in production settings. Now we ask the following question: how well is our model performance at serving time? The question is non-trivial because we do not have ground truth labels for serving data at hand. One possible solution is to use evaluation result on test data, but this may not reflect our model's performance on serving data truthfully because the serving data may contain errors that do not occur in training and test data, or there may be a distribution drift. Therefore, we choose to provide serving data to human experts for labeling. By comparing the human expert labeling results and the model prediction results, we can get a good estimation of our model performance. Since expert lab efforts is costly, we can only select a subset of data for labeling under limited financial budget. The goal of our work is to accurately estimate our model accuracy at deployment time with limited labeling budget. Before moving on to our framework, let's first consider entity resolution problem as a simple application, which motivates our evaluation metric selection. Here we have two source databases, D1 and D2. Our goal is to find a pair of instances from D1 and D2 that correspond to the same real-world entities. In entity resolution, the number of matches is usually much smaller than the matches in the candidate pool, so we are facing a class imbalance problem. In such cases, classification accuracy may give overconfident estimation of our model performance, and a commonly used metric is the F-score, which captures the model's precision and recall. We use the parameter alpha to control the importance of precision and recall, respectively. Now we briefly describe our framework. Our goal is to evaluate the F-measure of a binary classifier on an unlabeled dataset. Initially, we do not have ground truth labels, but we have model predictions on our dataset. We also assume the model can produce some scores denoting the probability of data belonging to the positive class. The scores do not need to be calibrated. For example, we can use the softmax output score from neural network models. Our framework adaptively selects data points based on their prediction results and scores and provides them to human experts for labeling. We can select subsequent data points based on the labeling result of previously selected data points. We also assume the human experts will always provide us ground truth labels. Finally, we suppose there is a fixed labeling budget, and after consuming our labeling budget, we want our estimation to be as accurate as possible. The key components in our framework are the adaptive sampler, which determines how to choose samples, and the estimator, which estimates F-measure based on current labeling result. We will discuss more about these two components later. Let's first consider a naive approach to solve this problem. The approach randomly selects a subset of unlabeled data and provides them to human experts for labeling. We estimate model performance on the population using its performance on selected subset. This method is consistent, but it has high variance. We can intuitively see this from the toy example. Here we use hook to represent true matches and smiley to represent predicted matches. Suppose the passive sampling selects 5 points to label. In the example, it only selects 2 from 4 predicted positives and 1 from 3 true matches. And the estimation of precision and recall based on such small subset will be quite unstable. 3 labeling budgets are given to true negative points, which do not affect precision or recall. The problem becomes worse when the class imbalance is more extreme, and most labeling budget will be given to true negative points. One lesson we learned from the toy example is that we should sample more from data points which are important for our estimation purpose. There are many prior works focusing on sampling more from important regions. They can be categorized into stratified sampling-based ones and importance sampling-based ones. Stratified sampling first split data into multiple strata, then perform passive sampling in each stratum separately. Sample allocation strategy decides how many samples are allocated to each stratum. Jack proposes to use proportional sampling when estimating F measure, that is, the sample budget is proportional to the size of stratum. But this method doesn't consider the variance within stratum. Neyman allocation allocates sample budget proportional to both strata size and standard deviation. It is known to be the best allocation method for estimating population mean. However, it is unclear whether it performs well in estimating F measure. On the other hand, importance sampling draws samples from an instrumental distribution, which is different from the underlying data distribution, and it assigns different weights to samples to correct the bias induced by sampling from instrumental distribution. The closest work to ours using importance sampling is OASIS. OASIS first derives an asymptotically optimal instrumental distribution, which minimizes the variance of a measure estimator, then samples from its stratified approximation. However, one limitation of OASIS is that it neglects strata variance when allocating samples, and this leads to suboptimal performance for finite labeling budget. We will discuss more about it in our experiments. As discussed, if our evaluation metric can be represented as population mean, we know that Neyman allocation is optimal. Observing the formula of F measure, we find that both true positives and false negatives can be represented as population mean, and the variance is easy to analyze. However, the F measure is a nonlinear function of true positives and false negatives, so its variance is much harder to compute. Here is a place where delta method plays a role. Essentially, the delta method says that if we have an asymptotically normal statistical estimator for parameter theta, and we have a smooth function g with non-zero gradient at theta, then we can get an asymptotically normal estimator for g theta, and we can approximately compute the variance of this estimator. Now we reformulate F measure as a nonlinear function of true positives and false negatives. When we split data into strata, we first split predicted positive instances with predicted negative instances. We use K+ to denote strata with predicted positive instances and K- to denote strata with predicted negative instances. P is the number of predicted positives, which is already known. As we have discussed, both true positives and false negatives can be represented as population mean. So we can use traditional stratified sampling approaches to derive an asymptotically normal estimator for them, and their variance can be easily computed. Now suppose X and Y are estimators for true positives and false negatives respectively. We can derive an estimator for F measure as a function of X and Y, and approximately compute the variance of our estimator using delta method. By minimizing the approximate variance of our estimator, we can derive a very concise sample allocation method, which we name the Fila allocation. The Fila allocation says that we should draw samples proportional to the product of strata size, strata standard deviation, and another factor, which we call class importance factor, because it describes how important the predicted positive strata and predicted negative strata are with respect to F measure. In our paper, we prove more properties of Fila allocation. We show that Fila is asymptotically optimal. It always has smaller or equal variance compared to Neyman allocation. And when precision is weighted higher, it is more preferred compared to Neyman allocation. Although we have derived the Fila allocation, we cannot directly sample from it because both strata standard deviation sigma k and class importance factor gk are unknown in advance. Here we are facing an explore-exploit dilemma. We need to draw more sample from strata with small labeling budget to get an accurate estimation of sigma k and gk. And we also want to draw samples according to the Fila allocation to minimize variance. So we modeled the problem using multi-armed bandits. We group data with similar output scores in the same strata with the additional requirement that split predict positive data with predicted negative data. Then we treat each strata as a bandit and treat each sample as a job from a bandit. There are many algorithms developed for multi-armed bandit. We select Thompson sampling and develop an algorithm named Phelan-Thompson that combines it with Phelan allocation. We further prove that the estimator derived by that algorithm is consistent. Analogous to Phelan-Thompson, we also propose an algorithm combining Neyman allocation with Thompson sampling. We name it Neyman-Thompson and compare it with Phelan-Thompson in our experiments. We perform experiments on 12 datasets. 8 of them come from entity resolution domain and 4 come from other domains, such as letter recognition and fraud detection. For each dataset, we evaluate the performance of a pre-trained classifier on it. The table at right shows the size and imbalance ratio of each dataset, and the type and the performance of corresponding classifier. We compare 4 methods: proportional sampling, OASIS, Neyman-Thompson, and Phelan-Thompson. For each dataset, we test these methods in 3 scenarios. Alpha is 0.1, where recall dominates. Alpha is 0.5, where precision and recall have the same weight. And alpha is 0.9, where precision dominates. We fix the labeling budget to be 300 or 3000, depending on dataset size. For each dataset, we repeat the experiment 100 times and report average statistics. This figure shows the average absolute error and standard deviation of the estimators over 100 runs in high precision scheme. Higher bar means lower absolute error and standard deviation. Phelan-Thompson performs best or equal best on all these datasets. You can see the results for high recall and balanced case in our paper. Now we dig deeper into one of these datasets to see how the estimator converges during adaptive sampling. In this figure, we plot the absolute error and standard deviation of the estimators as the sampling process goes on for the amazing Google dataset. Phelan-Thompson performs better for small labeling budget, as the absolute error and standard deviation drops quickly when labeling budget increases. The table at the left shows the average absolute error reduction of Phelan-Thompson compared to other methods on 12 datasets. Phelan-Thompson significantly outperforms OASIS in all scenarios, while its advantage over Neyman-Thompson mainly lies in high precision scheme. To understand the performance difference of these methods, we plot the average number of samples allocated to each stratum. This figure shows the average number of samples allocated to each stratum for the letter Volvo dataset in high precision scenario. The table below the figures shows the size and the label variance of each stratum. After observing the figure, we find that the main reason that Phelan outperforms OASIS is that OASIS neglects strata variance. For example, the brown line shows that the OASIS allocates about 50 samples to the last strata, but the strata has 0 variance, so a smaller sample size should be enough. This observation is also verified by inspecting the formula of OASIS stratified instrumental distribution, as we discussed in our paper. On the other hand, the advantage of Phelan-Thompson compared to Neyman-Thompson is mainly because Neyman-Thompson is not sensitive to the parameter alpha. As we can see, Neyman-Thompson allocates most budget to negative strata, which doesn't help in predicting precision. Phelan-Thompson combines the strengths of Neyman-Thompson and OASIS together, as it is both sensitive to alpha and strata variance. This explains why it always gives best or equal best performance on all datasets. We summarize our contributions as follows. First, we developed a label-efficient sample allocation method named Phelan to estimate F measure. We proved that Phelan is asymptotically optimal. Secondly, we designed an adaptive sampling algorithm named Phelan-Thompson to deal with the explore-exploit dilemma. Finally, we ran extensive experiments and verified that Phelan-Thompson produces more accurate estimation compared to state-of-the-art methods with small labeling budget. We also reviewed the limitations of previous methods by analyzing their sample allocation characteristics. Future directions include applying delta method to estimate other metrics and considering human expert labeling error. That concludes my presentation. If you are interested, please look at our paper or code for more details. Thank you.